So now let's get into a hands-on exercise. And throughout this exercise, I'm going to talk about the statistical concepts leveraged by Einstein discovery. You don't need to be a data scientist or statistician to gain further insight on data using Einstein discovery. However, it helps to be aware of the basic statistical concepts that we're leveraging to best interpret the results. And if you know anything about Salesforce, you'll know that trust is our #1 core value. And by showing you what we're doing on the back end, we hope that you'll be able to trust Einstein discovery when it provides you insights. I should start off by addressing that correlation is not causation. It is true that identifying correlations does not necessarily imply a causal relationship between two variables. And it's also true that Einstein discovery is looking for correlations in your data. But that's why it's important to carefully consider the variables you're including in your statistical model. With the appropriate variables, it's actually a stretch to assume that when we found correlation, there isn't any causation. The only way to actually prove causation is through repeated testing. Suppose we have this data here showing that shoe sales correlated strongly with the unvaccinated rate of children. If your boss came to you and said, hey, you shouldn't vaccinate your kids because that's going to increase shoe sales, you'd surely say that he's being ridiculous. This is purely correlation and definitely not causal. However, what if this wasn't shoe sales and was instead the admission rate of children to hospitals for vaccine-preventable illnesses? In this case, it's almost certain that some of this correlation is causal. In my marketing background, if I showed you a bar chart that showed that when we sent a customer a coupon, they purchased at higher rates, if you were to say that that's only correlation and not causation, what you're implying is that just by random chance, I happened to send the coupon to a bunch of customers who were already more likely to buy the product, and that sending the coupon had no impact on that decision. While it's certainly statistically possible that I did that, it is very unlikely that that's the case. The only way to confirm that sending the coupon actually impacted my customers' behavior is to try it amongst different subsets of my customers and observe that their behavior changed each time I did. But ultimately, I think it's a stretch to assume that when I sent the coupon to the customers and they purchased at higher rates, that it's pure correlation and no causation whatsoever. To follow along with these exercises, please visit this link. This is a special developer org that has the data preloaded for these exercises. For our first exercise, we're going to use a retail example. Retail examples work well because we're all consumers and we understand what drives us to make purchases. In Einstein Analytics, we have a data set called retail sales, which contains the daily sales volume of various products in various cities with various promotions and discounts throughout last year. We're going to use Einstein Discovery to plan a marketing campaign and optimize it. To access Einstein Analytics, use the app launcher within Salesforce. Then click on Analytics Studio. If we go to Datasets, you should see Retail Sales. To create a story with Einstein Discovery, click the menu option and click Create Story. As I mentioned during data prep, the first thing we have to do is identify what we're trying to maximize or minimize. So in this case, we want to maximize daily quantity. Note that you have the option of changing the story name. This is useful as you're iterating through stories and making changes. You should add a descriptive story name so that you know exactly what the story is. And you can add this to whatever app is appropriate. Data options is where you tell Einstein Discovery what variables to include and how to look at them. You can see daily quantity is a number, and that's our outcome variable. It identifies that we want to maximize it. Next is our date variable. If we scroll down in the options, you can see it's defaulting to analyze by month. If I click the drop-down, you can see my other options are day or year. If I select day, there are 365 values as this data set encompasses the entire year. That violates our limit of 100 values in a single variable. If I select year, there's only one year in this data set, so I'd have a bar chart with only one bar. That wouldn't be very helpful. So month is the appropriate selection here. If I scroll down, you'll see that I can also select day of week or month of year. If I have multiple years of data and I suspect there's some seasonality, I can tell it to look at month of year, which would determine if November is always better than the rest of the year or if it's just this one year. Similarly, with day of week, I can test whether or not Fridays always outperform the rest of the week or not. And scrolling further, I can change the date range. This is how I would subset by a date period. Suppose I didn't want to include December in this analysis. I could tell that the end date should be 11/30/2018, and then it would remove the December observations from the analysis. This saves you from having to create subsets of data when really what you want is to only analyze a subset. The next variable is city. If we scroll down, we can see all the cities included in this analysis and the frequency of those observations. If I uncheck some of these, a new category called Other appears. If you have categories that occur very rarely in your dataset, they might fall into Other by default. However, suppose that I don't want New York City or San Francisco in this analysis. If I scroll down further in Advanced Options, I'm given the option to either combine all into a new Other column or drop them from the analysis. So you do have the flexibility to subset by categories here. For this analysis, we're going to include New York and San Francisco. Finally, you'll see that the last option for a categorical variable is how to order the bars. By default, count is selected, and you'll see in the story the value of doing this. But if you want the bars sorted alphabetically, you do have that choice. For this exercise, we don't need to make any changes to our variables. So let's go to Review Settings and then create the story. When the story completes, the first chart you'll see is daily quantity by city. If your charts look compressed like this, one thing you can do is zoom out. So we gave Einstein Discovery 5 input variables, and we asked it how to maximize daily quantity. The first thing it's showing us is daily quantity by city. You'll see here that city explains 35.3% of the variation in daily quantity. 35.3% is an R-squared value, and that's why city is coming up first. It has the highest R-squared value. So let's talk about what R-squared is. To demonstrate R-squared, I'm going to use Python. Don't be afraid, I'm a professional. You don't need to know how to use Python to use Einstein Discovery. I just use this for demonstrating the statistical concepts. So what I have here are 5 data points. I have an x on the bottom, a y on the vertical axis, and you can see that as x increases, y does tend to increase. If we don't use x for our predictions here, all we'd have left is the y values. And what we would tend to do is use the average of the y values for our predictions. That's what this horizontal line is. It's just the average of the y values. You can see that as x changes, it's just predicting the constant average for all x values. When we talk about the errors of a prediction, what we care about are the vertical distances between the points and our prediction. So you can see here, for this point, the average didn't predict very well. But we can't just look at the errors. So this would be a large negative error, these would be large positive errors, and in fact with the mean, the average error is always 0. It's called an unbiased estimator for that reason. As a result, we have to look at squared errors, because if you square negatives, they become positives, and the negatives can't offset the positives in that case. It also has the benefit of allowing us to look at these as squares. So if we take all of these red squares and sum them together, you get a box that's 13.24 units squared. Another way to look at that would be a box that's 3.64 units on each side. Now if we use x for the prediction, you can see that as x increases, the prediction increases as well. We get these green boxes instead of the red ones. If we were to sum up the green boxes, we'd have a box that's 7.93 units squared, which would be 2.82 units on each side. If we compare these two boxes, you can see the green box is smaller than the red box. The error when we use x is smaller than the error when we don't use x. Specifically, the green box is about 60% the size of the red box, meaning we've reduced the error by 40%. And that's the R-squared value. But you're thinking, Randy, city isn't a number. How did we calculate an R-squared value for a city? Here's our data set. Sure enough, city is a categorical variable. But what Einstein Discovery does is it turns all these into true-false flags. Trues are 1s, falses are 0s, and then we can look at R-squared values. They look more like this, where all the values are either at 1 or 0, but we can still look at an R-squared value. Now, if you've taken a statistics course, they probably covered R-squared values. And it's also possible that your professor might have said something like, if the R-squared value is above 60%, it's a good model. If it's between 30 and 60%, it's moderate. If it's below 30%, it's a poor model. In the real world, this is actually nonsense. On the academic data that they work with, yes, they can obtain those R-squared values. But the real world is messy. So to demonstrate various R-squared values, I have this applet here. This would be an 80% R-squared. You can see all these points are very close to the line. As the R-squared gets less and less, you can see the points are moving away from the line vertically. And it gets to the point where if the line wasn't there, it might not be obvious that there should be a line at all. However, even here with an R-squared of 19%, that still means that using this variable has reduced the error by 19%. On business problems that involve human decisions, this actually isn't a very uncommon R-squared to see. So you shouldn't go into every use case expecting ultra-high R-squareds. The real world just doesn't behave so well. So that's where this 35.3% comes from. Einstein discovery looked at all the variables, it found that city had the highest R-squared value, and it's showing us that first for that reason. We could say that city has the strongest predictive impact on daily quantity. Now looking at the bar chart here, you'll see that we have New York City, Miami, Dallas, New Haven. Clearly these are not sorted alphabetically. As I alluded to earlier, these are sorted by frequency. So if I mouse over New York City, I'll see the count is 3,045. And if I mouse over Boston, you'll see the count is 2,989. The benefit of this is that I can see the bars that have the biggest impact on my business as they'll be towards the left. They represent a larger proportion of my business. You'll also note that New York City is a gray bar and the rest of the cities are blue bars. If you look at the legend, you'll see significant and insignificant. Ultimately, what this means is statistically significant and not statistically significant. So now we have to talk about what statistical hypothesis testing is. So to go back into Python, let's use a coin flip example. Suppose I flip this coin 100 times, ones are heads, zeros are tails, and this line here tracks the proportion of heads. If I look at the average after these 100 flips, I see that 65% of my flips were heads. I had 65 heads out of 100 flips. Now the probability that I would flip a fair coin and observe 65 heads is about 0.3%. If I had 1,000 people in a room flipping a coin 100 times, 3 or 4 of them might actually encounter this kind of outcome. But ultimately, if I had one coin and I flipped it 100 times and I observed 65 heads, the conclusion I would draw is that it's so unlikely that this would happen that the coin is not actually fair. That's what a statistical hypothesis test is doing. It's determining the likelihood that we would observe what we did under some hypothesis. So if you flip an actually fair coin, we observe a different result. In this case, the average is 47%. Now the question becomes, is 47% far enough from 50% for us to be skeptical of this coin? We can calculate the same probability and determine that you would get this kind of result about 48% of the time. This isn't that uncommon. So if I flipped a coin 100 times and observed 47 heads, that wouldn't provide evidence to suggest that the coin isn't fair. Now with our data set, we have our bars here, and you can build a bar chart in just about any analytics tool out there. But within this bar chart, we're doing hypothesis testing. So what we're doing is we're comparing New York City to not New York City. We're wondering, is this difference that we're seeing here statistically significant? Could this have happened randomly, or is it so unlikely that we have to say there's something different about New York? When we conduct that hypothesis test, we determine there's a 32% chance that we would observe this difference just randomly. That's not that uncommon. However, if we look at San Francisco, the probability that San Francisco would have an average so high compared to the rest of the data is 1.9 times 10 to the negative 267th. There's practically no chance that San Francisco would perform this well just randomly. So we do all of those hypothesis tests, and when we determine that one of the cities is not statistically significantly different, we color it gray. When we determine that it is statistically significantly different, we color it blue. So now that we see this, even though New York City is actually a little bit below the average line, there's nothing to be alarmed about. New York City is actually conforming to the rest of my business. There's nothing remarkable about it. However, San Francisco, Little Rock, and Boston are statistically significantly higher than average. Miami, Dallas, New Haven, Chicago, Honolulu, and Detroit are statistically significantly below average. But there's even more going on in this chart. If I mouse over San Francisco, you'll see that the text on the left highlights. It says that San Francisco is about 466 units above average. The result may have been worsened by promotion as mail-in. In my experience, most people don't like doing mail-in rebates. What this is alerting us to is that San Francisco is doing well, but it actually could have been doing better if they weren't doing mail-in promotions. Similarly, Boston is 458 units above average. The result may have been proved by discount as 10%. So Einstein Discovery went through all of my variables. It found that city had the most predictive power, and it showed me that first. It conducted statistical tests to determine which cities performed different than the rest, and it's also calling my attention to what we would call confounding effects. For San Francisco, mail-ins are hurting it, and for Boston, 10% discounts are helping it. So even though this is a simple bar chart, there's a lot more going on here. If we scroll down to the next chart, we see when date is 2018/11, or November, city is San Francisco and Boston do better. These are called drill-down charts, or two-variable bar charts. In this chart, all of the left bars represent the month of November for the respective city, and all of the right bars represent all other dates. Hypothesis testing works pretty much the same here. So we have our data set. We're calling out November for part of it, and then we're calling out everything that isn't November for its comparison. You'll see in this case, this is all San Francisco in November. This is San Francisco not in November. So those are the kind of tests we're doing. And across the board, the results are statistically significant. All of the left bars are blue. What that means is, in every city, November has higher sales than their other months in aggregate. So the natural question becomes, why didn't Einstein Discovery just tell me November performs well? Why is it adding this layer of complexity, breaking it apart by city? The reason is the magnitude difference. If I look at San Francisco, the difference between November and the other months is 1,238 units. However, for Chicago, the difference is only 393 units. It's still statistically significant in Chicago. November does perform better, but not nearly to the magnitude that San Francisco sees the benefit. So that's why Einstein Discovery added this extra layer of complexity. It's saying that November performs well, but it performs particularly well in certain locations. So we're doing all this statistical hypothesis testing, and there's this common misconception from people that took statistics courses that because they spent so much time focusing on standard normal probability tables, that statistical hypothesis testing only applies if the data is normally distributed. If statistics could only be done on data that's normally distributed, statistics as a whole would be pretty useless. There are all sorts of other distributions out there, and if we couldn't do statistics on them, we wouldn't be able to do much. For example, if you're counting the number of customers that walk into your store, that follows a Poisson distribution. If you're looking at how long it takes before the next customer walks in, that's a chi-square distribution. There are endless other distributions out there. However, the most important theorem in all of statistics, in my opinion, is the central limit theorem. So to demonstrate, we'll go back to Python. The central limit theorem states that if I take a sample from any population and I calculate the mean of that sample, the mean follows a normal distribution. I have a uniform distribution, meaning that every x value is equally likely to be drawn from this population. If I take a sample from this data set and calculate the mean of the sample, I get 5.53. It's no coincidence that it's towards the middle of my population. Now, what the central limit theorem says is if I take all possible samples from this distribution and calculate the mean of all of those samples, these means will follow a bell curve. Now, I don't have the compute power or time to take all possible samples, but I can take 5,000 of them to demonstrate this concept. So starting with this data, I took a sample, calculated the mean, and I did that 5,000 times. And if I look at the distribution of those means, this is what I get. This is a normal distribution. I'm going to drive this point home a little bit further. I have this bimodal distribution, which is almost the inverse of the normal distribution. The extrema are more likely than the center. This is actually a very common distribution to see in real-world data, because if you conduct surveys, your happy customers want to reply, your angry customers want to reply, but the people in the middle really don't care to reply. Applying the central limit theorem to this same distribution yields the same bell curve that we expect. This is the central limit theorem at work. No matter what distribution your data follows, the mean follows a normal distribution, and that allows us to perform statistical hypothesis tests on it. This also relates to the sample size discussion we had before. If I take relatively small samples, I end up with a pretty wide distribution. So if I'm using small data samples, I would guess that the true mean is somewhere between maybe 5 and 7. But as I take larger and larger samples, you'll see that the bell curve becomes more narrow. Larger data allows us to be more confident about where the actual mean is. So that's also why you should use as much data as possible to answer your business questions. It allows you to be more confident about the results you're getting. And if I calculate the actual mean of my population, I'd see it's 5.86, which is right at the center of my bell curve. If we scroll down a little bit further, we arrive at daily quantity by date. So sure enough, as we just saw, it is calling my attention to the fact that November does perform well. Highlighting over this point, you see on the left, November is about 468 units above average. The result may have been improved by promotion as coupon. Now, if you think back to when you're shopping throughout the year, I suspect you know what's going on here. In November, we have huge sales like Black Friday, Cyber Monday, and whatever the heck we're calling shopping on Thanksgiving these days. Einstein Discovery is alerting me to the fact that November is being impacted by a change in promotion, specifically coupons. So now we can go deeper. I want to ask Einstein Discovery how coupon is having an impact on November.